Okay. We left off last time after we found we analyzed Gauss's law for a point charge and for a conducting sphere. And for the entire sphere is conducted. Now, what we're going to do now, and we created actually with the conducting sphere, we created real piecewise functions. You guys remember that? That's where we left off, where we had the graph that was here, and it climbed linearly, and then it declined with 1 over r squared. And so that was, you will see this graph. I mentioned this to you. And this climbing linearly, and a 1 over squared drop off is also similar to what would happen to the acceleration due to gravity if you were inside of a massive sphere. And you may see a problem like that coming in your future. So, and yeah, yours appears at that point. So, but now we're going to talk about a shell. So we have a sphere, but it's only the outside of the sphere. Okay, so now we're talking about a sphere, but we're only talking about an outside of the sphere that is very thin. For purposes of that we're talking about, the shell is impossibly thin, like infinitely thin, because otherwise you start dealing with difference in radii of the inner and outer thickness of the shell. So, all right, so we're going to examine 2 cases again. We're going to examine, here's our shell. And on a shell, the charge is only out at the surface. They're only out on the surface of the shell. This has a radius, capital R. And we're going to examine 2 situations. We're going to examine examine the field where our radius is bigger than R. But if radius is bigger than R, then we just create a Gaussian surface around the whole thing. And we've already figured out that's a trivial answer, that our E is KQ over R squared. Right, so this is, if we can create the Gaussian sphere and a symmetric sphere around any particular object, where it has a spherical symmetry, then we can just treat it like a point charge. Okay, if it's inside, now if we have something that is on the inside, this is interesting. Gesundheit. Okay. If we want to examine the inside, then we must write, of course, E equals integral of E dot dA, which equals Q enclosed over epsilon naught. Well, if our charge, right? Or I'm sorry, the area of our sphere inside of this. So let's draw this in here. So if we have our sphere, and it goes back, and it's on the front, and it goes back. There's our sphere. Really, really poorly drawn sphere, but that's okay. And this is little r. The surface area of our sphere is going to be 4 pi r squared. So this is going to be the total amount of field, times 4 pi r squared for our dA for our Gaussian surface. And that equals, however, the Q enclosed over epsilon naught. But how much charge are we enclosing? 0. It's all outside the sphere, right? Q enclosed equals 0. Okay. Then E 4 pi r squared equals 0. And, well, we know the radius doesn't equal 0. So it's got to be the field. So the field inside a sphere, a shell of charge, equals 0. And this is a pretty profound idea. So the charge inside, so if it's uniformly distributed throughout the sphere, throughout the volume of a sphere, then we're going to have, then we have our increasing charge to the surface, and then it decreases 1 over r squared because of a Gaussian surface around it. If there's no charge inside, there's no charge to enclose in a Gaussian sphere. Therefore, there's no electric field inside the sphere. And this is important. This would be similar to, now this would be cool. Imagine a hollow massive sphere that has the same mass of the Earth, but all of the mass is on the crust of the planet. Okay. Inside that crust, where would the gravity be? There would be no gravity inside of the massive sphere. It would be free to float around inside. If all the mass was on the surface, concentrated on the edge, it was hollow on the inside, there would be no gravity.
No air?
Yeah, yes, and that's a good question. So let's say you're right here. Let's see. You mind you, the intent for me mentioning gravity is that the charge and the gravity are analogous with each other because of Coulomb's law and universal gravitation, right? Okay. So let's say you're right here. I'll even call it negative. The closer you get to this side, is counteracted by the fact that you have so much more charge on the other side. And so now I'm not going to do that, but I will tell you that it's a proof in your book, and you're welcome to look at it. But the volume, the amount of the rate of change of surface area of the charge around it, or the rate of change of mass around on one side of the charge, is based on the surface area, which is proportional to r squared, which is, and the distance that you have from the mass on the other side is also proportional to r squared, and so it just redistributes evenly. That's really how you go about it. So it redistributes evenly. So anything inside of the shell, there's no field value for anything inside the shell. It's a pretty profound idea. So that is the shell. That's sort of a trivial case when it comes to our field laws here. The next one I want to go over is a cylindrical charge. Okay, so we have a cylindrical charge, or we're in particular talking about cylindrical symmetry, which is a difficult word for me to say. Cylindrical symmetry. We're going to create a wire, or for our intents and purposes, an infinitely long rod of charge. Infinitely long. A really, really ridiculously long rod of charge Q. You get what I'm saying? Okay. So, if we turn it into a sketch, it'll cover it up. Okay. So if we so here's a really, really long rod with a whole bunch of positive charge on it, and our charge, okay, it has a charge density then of lambda. It's okay with clicking the margin. Right. So you will be given lambda, by the way. Do that, or you will be asked to determine lambda given the other information. So that's all right. Now, the reason we use terms like forever is so that we don't deal with end effects. So imagine imagine if you had this and there was an end to it, then at the end you're going to start getting curved field lines, and we don't want to don't want to bother with those. That makes our calculations more difficult, and that's the last thing that we need to be doing. So around our rod here, I'm going to turn this into just a line. Okay. We don't really have realistic, and all the time, because we're talking about protons and electrons here, right? Protons are the positive charge, electrons are the negative charge, and so there is no true mathematical line, and we have to pay attention to that when we're doing the math for this. However, I will tell you, and please have faith, that if we just turn this into a mathematical line with a charge value to it, it doesn't affect our calculations here. So, but if we have a test charge right here, what would the forces be like on it? The field line. Right? So the field lines are going to be the direction of the force. So this one over here, this charge is going to give it a force in that direction, and this one's going to give it a force in that direction. This one's going to be more like that, and this one's going to be up, and this one's going to be over, and okay. Which means that for any one particular spot along your infinitely long line, it's going to be radially out from the line, right? So, what if we take our line and we look at it from the end? Okay. So we take our wire and we poke it into our eye, and we're able to see our electric field, and here's our wire, right? Okay, with our static charge. What is the field line going to look like? And field lines are going to go radially out, right? So if we take it, so we're looking here. If we're looking sideways from our line, our field lines are radial, but if we can like take a sheet of paper here and like this, it would be perpendicular to our sheet of paper, right? At any particular point, or actually, there would be if the plane is like tangential to the line, where that there would be a normal line coming out of it, and then lines spreading out through it. But if we take a cylinder around this, we draw a cylinder around this, then all of a sudden, any particular direction we have our field lines coming out. Okay. DA, and this is our E. Okay. So we have a similar sort of thing, right? But our E dot DA are going to be in the same direction, so we can get rid of the whole dot product and get rid of that. One of our goals when we're doing this is to get rid of that complicated math. So here's our sphere. Okay, and this could be like in microcoulombs per meter, whatever we want to call it. But we wind up with, let me bring it back up here. Integral of E dot dA equals Q enclosed over epsilon naught. Okay. And remember the cylinder, the reason we have cylinder, we talk about infinitely long, so we don't have end caps, we're not worried about end caps. Okay. But how much? Oh, and also we can forget the end caps because what's going to be the flux? Here, let's draw our, here's our line here. Okay, let's draw a cylinder around the line. This is going to be a little better. Let's put a little more. Okay. Here at the end, what's going to be our flux to the ends of the cylinder? If it's the right cylinder. Nothing. Right? Because the lines would have to come out perpendicular to the end of the cylinder, and we have an infinitely long line, so they're all going to come out radially. So there is no end effect for a cylinder because there's no flux to the end. Okay. But what we can do then is start figuring this stuff out. What's going to be our area as we integrate area over the surface, what's going to be our total area of our cylinder? Well, if we ignore the end, then it's the circumference times the length, right? Hold on a second. All right. So, right. So the circumference of our sphere is just going to be pi r squared, or 2 pi r, right? Okay. Times the length of the charge that we're enclosing. Our area is just going to be this is going to be between E 2 pi r. That's going to be our area for our cylinder. And this is going to equal the charge enclosed. Well, if this has a charge density lambda, a linear density lambda, and we're talking about the charge over the entire length, then that's just going to be lambda L over epsilon naught. Well, we can start, if we're solving for E, then we can start canceling things so that L's are going to cancel. And this winds up being E equals, there's two ways of looking at this. This could either, I want you to get in the habit of pulling the constants out and leaving leaving the variable inside of the parentheses, or separating the variable from the constant. So this is going to wind up being lambda over 2 pi epsilon naught times 1 over r. And what this is telling you is that as we move away from our linear charge, the field will decrease with 1 over the radius. It's a linear decrease. Changes linearly rather than r squared. Okay. There's another way we could have read this, and this could have been we could turn this into k. And this could have been k, and that would be lambda k over 2 lambda k over r, 1 over r, because this is 1 over 4 pi. 1 over 4 pi epsilon still equals k, right? Or 9 times 9. So that's another way of looking at this. If we wrote it with k. Okay, so that would be a cylinder. There's one last one that I want to show you guys. That is, no, that was just if we had. Oh, this is the situation if r. Sorry, guys. The first situation is these are the two situations we're in. This is if r, the radius of our sphere of our surface is greater than the radius of our line charge. Okay. Now we're going to expand our line charge, and we're going to be inside the line. So we're going to do r is less than r. All right. So the math remains very much the same. We still have the integral. D dot dA equals. You guys catch anything here? Not just the green, but we're writing this over and over and over again. Use you'll get a point for it. It's worth writing for. Okay. But instead of, and I'm just going to go back and take this, I'll alter this one. So instead of this being surrounding, we're going to turn this around right here. This is the line charge. And the positive charge is distributed uniformly throughout this cylinder. It means we are inside of it now. So we have the same stuff. We still have E equals E is the 2 pi r times the length, because that's still the surface of that's still the volume. Wait, no. then still the area of our surface here, we're still going to have no charge coming outside. Okay, so it works like that. But that's now going to equal, okay, our charge. We don't get to use lambda anymore. We now need to use rho again as a volume density of charge because we need to find the volume of our volume of the cylinder. So our Qn is going to equal the area of our cylinder, which is pi r squared L. Um, because that's the volume of our cylinder. That's our rho. So this is our total Q in charge. So that's going to equal rho pi r squared L on that. And now we start canceling again. L is going to cancel. R is going to cancel one of the R's here. Pi is going to cancel. So our field becomes 2 rho on that R. Oh, there's that. Yeah, she's on the bottom. You guys see the cancel? See what we did there? So the point for showing you guys this is pay attention to your volumes, pay attention to your areas, but it's really not that tough because you get to start canceling stuff. If you choose the right surface, it becomes very straightforward. Which brings us to the last one. The big R was the radius of our total charge of the cylinder. So we're going to drop from the end, right? So this is R. And then our Gaussian surface was inside of it, little r. And we did this for our little r being less than big R. Now, what happened? What about all the charges outside of it? Right. It's like it's the shell idea. If you have a hollow spot inside the hollow, there is no effect from what's outside. I've been doing. What I suggest to you is make your big R. Your big R is the radius of your object, and your little r is your variable, whether you're inside or outside the sphere. The little r is the Gaussian surface we've been using. So this brings us to our last one, which is a charged plane. Okay, so we're not going to get to a conducting material, but that's okay. That is really okay. So assume we have a plane here, and our plane is infinitely wide in all directions, which of course this does not exist in the universe. But okay, this is my world, and I'm saying that it's okay right now. We assume that it's infinitely wide because we don't want to deal with end effects. Our plane, positive charges. What is the field going to look like near the plane? It's all going to be perpendicular to the plane. You're not going to have any charges that are off to the side. Actually, if that were to happen and you were to bring a test charge near it, it would cause an acceleration. We would no longer have what's called an electrostatic condition, which is what all these are based on. These are all based on charges that aren't moving. And so all of these The point is that they're extending the field to both sides. So we're gonna pick a surface, and it really doesn't matter which one. I'm just gonna pick one that only has one variable for a Gaussian surface. It's easier to integrate. So we're going to pick a cylinder or a circle. And here in the surface, it looks like that, and then if it drops below, here's our cylinder that's passing through this. Yeah? It's going to have a radius r, and the charge density inside here is going to be represented by a sigma. You remember area sigma for unit area. So we gotta rip through the same thing here. So what's gonna happen here? We have E dot dA, but we're talking about flux here, right? If our flux is perpendicular to the plane, and we could choose a cylinder that is perpendicular to the plane, is there any flux going out the side? Huh. Is there any flux going out this way or that way? Side of our cylinder? So the only flux that we're dealing with is coming out the top of our cylinder or coming out the bottom of the cylinder. Yeah? Okay. So what is the area we're dealing with? This is just going to be E. I'm sorry. I was going to draw an equal there. It's not equal. E times what is this is Q enclosed. That's on that. What are the areas we're dealing with? Well, we have an area on top, right? Yeah. So the area on top would be pi r squared, but we also have an area on the bottom, right? Also pi r squared. So whatever area you choose, because it doesn't really matter, we're just going to call it 2 times the area. Whatever, but you could use an amoeba. It doesn't matter. A circle is just easier to draw. But that's going to equal our sigma times the area times that same area, right? Well, not. Well, here's the beauty of it. Areas cancel. So if you have plane symmetry with over a flat plane, electric field equals sigma over 2 epsilon naught. That's it. So it's your area charge density over 2 epsilon naught. That is your